Okay, welcome back. We are going to start with empirical probability, okay? And then we'll move on to some rules. Okay, so the difference between classical probability and empirical probability is that, as I mentioned, classical probability will assume that the outcomes are equally likely, right, for, in every experiment, while empirical probability relies on actual experience or actual data, okay, to determine the likelihood of outcomes. All right, so you actually, take a survey, gather data, then out of that, okay, you can determine the probabilities. You are not assuming that every outcome is equally likely, and you are not necessarily using sample spaces. So in empirical probability, you might actually, do the experiment itself, roll a given die maybe 5,000 times or 10,000 times, and observe the various frequencies and use them, okay, to determine the probability of an outcome. Okay, so you don't have to do that under classical probability, but that is done under empirical. Okay, so suppose, for example, that a researcher asks 25 people if they like the taste of a new soft drink. Okay, and then the responses were classified as yes, no, and undecided, I'm not sure. Okay, and these are the results. 15 people said yes, 8 people said no, and 2 were undecided. If you add them, you have the 25 people. Okay, so out of these frequencies, all right, you can find the probability of those who said yes, the probability of those who said no, and then the probability of those who were undecided. So that is the concept of empirical probability. So you can then compare the different probabilities. For example, the probability of selecting somebody who said yes will be, if you like, 15 out of the total number of 25. Okay, which is the same as 3 or 5. So that is a concept of an empirical probability. So the formula for computing empirical probability is probability. Okay, the probability of the event is the frequency, right, for the class over the total frequency. So in this case, for those who said yes, probability for that class will be 15 people, and the total is 25. All right. So if you do that, you compute what is called the empirical probability, which is based on, if you like, actual observation or experience. So in the soft drink survey that we just looked at, what is the probability that the person responded no? So you look for the number of people who said no and divide by the total number. 8 people said no, so take 8 over 25, and that will give you that probability. Okay. Okay, good. So here's another example. In a sample of 50 people, 21 had type O blood, 22 had type A blood, 5 had type B blood, and 2 had type AB blood. Okay, so the question is asking to set up a frequency distribution like the one we just saw, right? Like this, okay, frequency distribution for the different types of blood and the number of people who have those types. All right. Okay, so after you set up the distribution, you find the probabilities of a person. What is the probability that person has type O blood? A person has type A or type B blood. A person has neither type A nor type O blood. And a person does not have type AB blood. Okay, so we'll look at these examples to help us understand empirical probabilities and how you compute them. Okay, well, so let's set up the frequency table, distribution table. For type A, there are 22 people. Type B, there are 5. There are AB, there are 2. Type O, there are 21. Okay, so and this seems people in type A and O are the majority. If you add all of these, you should get 50. All right, so that's important. Okay, good. So find a probability that a person has type O blood. Take the number of people who have type O and divide by the total number. That will give you that. All right. So that gives you 20 out of 50. A probability that the person have type A or type B, okay, will be the sum. When you see or, it means sum of the probabilities of those who have type A and type B. So A will be 22 over 50, type B will be 5 over 50, that gives you 27 over 50. And then C says, find a probability that the person has neither type A nor type O blood. Well, if they don't have A nor O, then they would have B or AB. So you take the probability of B and add it to that of AB. Okay, so the language is important. It's important to understand how it is phrased. So B will be 5 over 50, AB will be 2 over 50, and that will be 7 over 50. All right. Okay, then the last one says, find the probability that the person does not have type AB blood. Well, if they don't have type AB, then they have the other ones, right? They either have A or B or O. So you can add all of those up. The probabilities are going to give you this. Or the easier way actually is to find the probability that the person has that AB and subtract it from 1. Okay, because you are looking for the complement of AB. Okay, I think that's what we did here. So take 1 minus the probability that the person has AB. AB is 2 out of 50, so subtract from 1, and that gives you 48 of 50 or 24 or 25. All right, so there are 2 ways you could do it. So if you do it this way, you could try the other way, where instead of AB, take the probabilities of the other ones. 22 plus this 27 plus 21. That will give you the 48 over 50. Okay. All right, good. All right, here's another example. A hospital records, indicated that maternity patients stayed in the hospital for the number of days shown in the distribution table. Okay, so number of days stayed, this is 3 days. So the number of maternity patients who stayed for 3 days in the hospital, all right, are 15 people. Number of those who stayed for 4 days in the hospital are 32 people, and so on. Okay, right? The total number of people will be 127. Okay, so you want to find these probabilities that the patient stayed exactly 5 days. Okay, so how many stayed for 5 days? That's 56. So take 56 out of the 127. And then you want to find the probability that a patient stayed less than 6 days. If they stayed less than 6 days, then the other stayed for 3 or 4 or 5. You take these and add them. So you take 15 over 127, 32 over 127, 52 over 127, and add them up. All right. The patient stayed at most 4 days. All right. So 4 or less. So the other stayed 4 or 3 days. So you take these 2. And then the patient stayed at least 5 days. All right. So 5 or more days. So that will be 5, 6, and then 7. Okay. So you can look at all of these. So the first one is easier, is the easiest. Exactly 5 days will be 56 out of 127. They stayed less than 6 days will be the stayed for 3 days. That's 15 over this, 4 days, and then 5 days. So you add them up and you get that. They stayed for at most 4 days. So 4 or less. So 4 and 3 days. That gives you that. And then at least 5 days. So 5 or more. So 5 days, 6, and 7 days. You add them up. 6 over 56, 19, and then 5. Let's see this. Okay. So that's how you compute the probabilities from a frequency distribution table. Note that empirical probabilities can also be found when you use a relative frequency distribution. All right. So in other words, you could put the probabilities right as relative frequencies. So you take the example we showed before, right? Those who said yes, no, and undecided. You take 15 out of the 25 will give you the relative frequency of 0.6. 8 out of 25 will give you 0.32. 2 out of 25 is 0.08. If you add all of this, you should get 1. So these are basically probabilities. The sum should give you 1, right? As we saw in one of the rules. So the probability that a person responded yes can just be picked, or no can just be picked from the relative frequency. That is just 0.32. All right. And this is actually equal to the 8 over 25 that we computed before. Okay, so you could use this as well. This is an alternative way of computing the probabilities. Okay, so in the next couple of lectures, we'll look at the so-called law of large numbers, and then we'll look at some the addition rules and the multiplication rules of probabilities. All right, empirical probabilities. That's what we'll do next.